Hello friends, the topic of today's discussion is position of signals or chemical shift in NMR, particularly in proton NMR. In this, we will discuss mechanism of nuclear magnetic resonance, position of signals or chemical shift, factors affecting chemical shift, and general regions of chemical shifts for different protons. Before discussing chemical shift, it would be better to first know about the mechanism of nuclear magnetic resonance. Suppose this sphere represents a nucleus. This is nuclear axis around which the nuclear spin occurs. If we view the nucleus from the top, it would look like this, where a red dot represents nuclear axis. Now, we can visualize nuclear spin about the axis more clearly. When an external magnetic field is applied, the orientation of rotational axis of the nucleus changes. This is the previous axis. Here, the nucleus continues to rotate around its axis, and additionally, the nuclear axis starts rotating around the previous axis. This can be visualized like this. The frequency of rotation of the nuclear axis around the previous axis is called angular frequency or precessional frequency or Larmor frequency. The precessional frequency is directly proportional to the applied magnetic field. Means the stronger the applied magnetic field, the higher will be the precessional frequency. For a proton, if applied magnetic field is 1.41 Tesla, the precessional frequency is around 60 MHz. Since the nucleus has a charge, the precession generates an oscillating electric field of the same frequency. In NMR, we use magnetic field as well as radio frequency waves. When the frequency of oscillating electric field component of applied radio frequency waves matches the frequency of the electric field generated by the precession of the nucleus, energy is transferred from the radio waves to the nucleus that cause transition of nucleus from lower state to higher state, giving rise to absorption peak. This is called nuclear magnetic resonance. We can simply say that for the resonance to occur, the precessional frequency of the nucleus should be equal to the radio frequency applied. Now we will discuss chemical shift. Protons in a molecule are surrounded by electrons and can exist in slightly different electronic environment from one another. The valence shell electron densities vary from one proton to another. The protons are shielded by the electrons that surround them. When an external magnetic field B0 is applied, these electrons are caused to circulate. Since the electrons are charged particles, so their circulation generates a local magnetic field B called induced magnetic field or secondary magnetic field. Here we can see that the direction of secondary magnetic field is opposite to the applied magnetic field. So the net magnetic field experienced by the nucleus will be equal to B0 minus B. Or we can say that the net magnetic field experienced by the nucleus will be less than the applied magnetic field B0. So the precessional frequency of this proton will be less than if it would have experienced B0. Or we can also say that precessional frequency of this proton will be less than a naked proton. Therefore, it will resonate at a lower value of radio frequency compared to a naked proton. Thus, protons in a molecule having slightly different electronic environment will resonate at different radio frequencies. These differences between the radio frequencies is very small. For example, the difference between the resonance frequencies of the protons in chloromethane and fluoromethane is only 72 Hz in a 60 MHz NMR instrument, which is 72 Hz upon 60 MHz is equal to 1.2 ppm. It is very difficult to measure the exact resonance frequency. So, no attempt is to measure the exact frequency. Instead, a reference compound is placed in the solution of the substance to be measured, and the resonance frequency of each proton in the sample is measured relative to the resonance frequencies of the protons of the reference. The difference between the absorption position of a particular proton from the absorption position of a particular proton of reference compound is called chemical shift of that particular proton. So, we can write chemical shift in Hertz is equal to radio frequency in Hertz at which a particular proton in the sample resonates minus radio frequency in Hertz at which proton in the reference resonates. We can also represent this chemical shift in Hertz as delta nu. The standard reference for the proton NMR, which is universally used, is tetramethylsilane, also called TMS. The reason for choosing it as a reference is that it has very shielded protons. All the 12 protons are in the same environment. This is chemically inert and has low boiling so that it can easily be removed from the sample. Chemical shift in Hertz is field dependent. In an applied magnetic field of 1.41 Tesla, a proton resonates approximately at 60 MHz, while in an applied field of 2.35 Tesla, it resonates approximately at 100 MHz. Here, we can see that 100 upon 60 is equal to 1.66 and 2.35 upon 1.41 is equal to 1.66. So, we can say that the ratio of frequencies are the same as the ratio of applied fields. Thus, chemical shift of a particular proton in Hertz in a 100 MHz instrument is 1.66 times greater than in 60 MHz instrument. This can create confusion while comparing data recorded on the instruments that differ in strength of the magnetic field. This confusion is overcome by dividing shift of a given proton in Hertz by frequency of the instrument in megahertz. This chemical shift is denoted by small delta. So the chemical shift delta will be equal to shift of a given proton in Hertz upon frequency of instrument in megahertz. Since the shift in Hertz, the shift is in Hertz while instrumental frequency is in megahertz. So the value of chemical shift delta will be in ppm. The value of chemical shift in ppm is independent of instrumental frequency. Now let's solve few problems based on this formula. Question number 1. The signal for OH in the 1H NMR of benzyl alcohol in a 60 MHz NMR instrument was found to be at 144 Hz higher frequency than TMS. Calculate the chemical shift of OH proton in ppm. Given that chemical shift in Hertz, that is delta nu is equal to 144 Hz, instrumental frequency is equal to 60 MHz. We know that chemical shift in ppm is equal to delta nu in Hertz upon instrumental frequency in megahertz. So chemical shift will be 144 upon 60 ppm, that will be equal to 2.4 ppm. Question number 2. The signal for CH2 protons in the 1H NMR of benzyl alcohol in a 300 MHz NMR instrument was found to be at 4.6 ppm. Calculate the difference in frequency expressed in Hertz between this and TMS signal. Chemical shift in Hertz, that is delta nu, we have to know. Instrumental frequency is equal to 300 MHz. Chemical shift in ppm is 4.6. We know that chemical shift in ppm is equal to delta nu in Hertz upon instrumental frequency in megahertz. So 4.6 is equal to delta nu upon 300, or delta nu is equal to 4.6 into 300, that will be equal to 1380 Hz. Range of chemical shift in 1H NMR on delta scale. The chemical shift in proton NMR on delta scale ranges from -10 to 30 ppm, but majority of organic compounds have their chemical shifts between 0 to 10 ppm. By convention, the delta scale runs from right to left with the increasing values, and chemical shift of TMS is designated as 0. Magnetic field increases from left to right. TMS protons are highly shielded and have 0 delta value. Shielded nuclei tend to resonate at higher magnetic field and have lower delta value, which is called off-field shift. The resonance of these nuclei requires lower frequency. Conversely, de-shielded nuclei tend to resonate at lower magnetic field and have higher delta value, which is called down-field shift. The resonance of these nuclei requires higher frequency. Now we will discuss factors affecting chemical shift. There are several factors that affect chemical shift. We will discuss one by one. Electronegativity. Electron withdrawing groups, when attached to another group, withdraw electrons that causes deshielding. As a result, value of chemical shift increases. In contrast, electron donating groups donate electrons that causes shielding. As a result, chemical shift decreases. For example, in this table, all the 5 molecules have a common CH3 group, but the CH3 is attached to different groups in different molecules. This is the electronegativity order of these groups. We can see that the chemical shift of CH3 is in the same order. Chemical shift increases with the increasing number of electron withdrawing groups. For example, in this table, the chemical shift of proton increases with the increasing number of chlorine atoms. Let's have the example of cyclohexanone. In this, we have to predict whether alpha or beta proton has higher chemical shift. The picture will be more clear if we draw the resonating structure. We can draw the resonating structure of cyclohexanone like this. Here we can see that due to resonance effect, beta carbon is more electron deficient than alpha. So beta proton will be more deshielded and thus will have higher chemical shift than alpha. The observed value of chemical shift of this alpha proton is around 6 ppm, while that of beta is 7 ppm. Let's have the example of 3,4-dihydro-2H-pyran. In this case too, we have to find the relative chemical shift of alpha and beta protons. We can draw the resonating structure like this. Here, we can see that beta carbon has greater electron density. So, beta proton will be more shielded than alpha. And thus, beta proton will have less chemical shift than alpha. The observed value of chemical shift of this beta proton is 4.7 ppm, while that of alpha is 6.4 ppm. Nitrobenzene. It gives 3 signals in the proton NMR because of 3 sets of protons, ortho, meta and para. Nitro group pulls out electrons from the ring by both the inductive and mesomeric effects. Let's draw the resonance hybrid to see the effect of electron withdrawal due to mesomeric effect. Here we can see that ortho and para protons are more deshielded than meta. So ortho and para will have higher chemical shift than meta. Ortho proton will be more deshielded than para because of greater inductive effect as it is closer to the nitro group. So the order of chemical shift will be like this. The observed chemical shift values for ortho, meta and para are 8.19, 7.51 and 7.65 ppm respectively. Anisole. It also gives 3 signals in the proton NMR because of 3 sets of protons, ortho, meta and para. Methoxy group acts as electron donating group via mesomeric effect, while as electron withdrawing group via inductive effect. The mesomeric effect dominates over inductive effect. So, overall effect of methoxy is electron donating. Let's draw the resonance hybrid to see the relative electron density on different carbons. Here, we can see that ortho and para protons are more shielded than meta due to partial negative charge. So, ortho and para will have lower chemical shift than meta. Mesomeric effect is slightly higher on ortho than para. So, ortho will be slightly more shielded than para. So, overall shielding order will be ortho, then para, and then meta. Thus, the chemical shift will be lowest for ortho. Para will have higher chemical shift than ortho, and meta will have highest chemical shift. The observed chemical shift values for ortho, meta, and para are 6.88, 7.25, and 6.92 ppm. The second factor that affects the chemical shift is degree of carbon. Chemical shift of a proton tends to increase when there is increase in the degree of carbon to which it is attached. This is evident from this table, where we can see that methane has chemical shift for proton at 0.23 ppm. Ethane with primary carbon has chemical shift of 0.96 ppm. Propane has chemical shift of 1.3 ppm for the CH2 protons which are attached to the secondary carbon, and in isobutane the proton is attached to the tertiary carbon that has chemical shift of 1.4 ppm. Third factor is esthetic factor or van der Waals deshielding. If the molecular geometry is such that it forces a proton to be close to some other functional groups, the proton is generally deshielded due to repulsion between electron cloud of functional group and the electron cloud of that proton. For example, cyclohexane derivatives A and B. The proton attached to the carbon bearing OH in compound B resonates at 3.6 ppm, which is downfilled by 0.31 ppm compared to the similar proton in the model compound A. This is because the axial methyl repels the electron cloud of the proton shown in green and thus causes deshielding. Similar explanation can be given for C and D and E and F. Hydrogen bonding. When there is hydrogen bonding, the electron cloud around the proton is decreased and thus causes deshielding of the proton. This result higher chemical shift. The stronger the hydrogen bond, the higher will be the chemical shift. This is the reason why signals for labile protons like OH and NH move downfield in the hydrogen bonding solvents like DMSO or acetone. We can distinguish between intramolecular and intermolecular hydrogen bonding using proton NMR. For this, NMR spectrum is recorded in solvents like CCl4, CdCl3, C6D6, etc. that are not capable of forming hydrogen bond with the compound at different concentrations. Dilution doesn't have any effect on intramolecular hydrogen bonding. So there is no dilution effect on the position of signals if there is intramolecular hydrogen bonding. In the case of intermolecular hydrogen bonding, extent of hydrogen bonding decreases with the increasing dilution. So if there is intermolecular hydrogen bonding, signal for the labile proton will show upfield shift on increasing dilution, or we can say decreasing concentration. The fifth factor is anisotropic factor. I am not going to discuss this factor in this video because I have uploaded a separate lecture on this topic. The link for the same is given in the description of this video. General regions of chemical shifts for non-labile protons. Aldehyde protons appear between 9 to 10 ppm. Aromatic or heteroaromatic protons between 6 to 9 ppm. Alkenic protons between 4.5 to 7.5 ppm. Alpha disubstituted aliphatic protons between 2.5 to 7 ppm. Alpha monosubstituted aliphatic protons between 2 to 5 ppm. Alkyne protons between 1.5 to 3.5 ppm. Beta substituted aliphatic protons between 1 to 2 ppm. And aliphatic and alicyclic protons between 0 to 2 ppm. General regions of chemical shift for labile protons. Protons attached to heteroatoms like oxygen, nitrogen and sulfur come under the category of labile protons. These protons are OH, NH and SH. OH is present in alcohols, enols, phenols and carboxylic acids. In alcohols, OH proton resonates between 1 to 5 ppm. In enols, between 10 to 17 ppm. In phenols, between 4 to 11 ppm. And in carboxylic acid, between 10 to 14 ppm. NH proton is present in amines, anilines, amides and ammonium salts. In aliphatic amines, NH proton resonates between 0.5 to 3.5 ppm. In anilines, between 3 to 5 ppm. In amides, between 4 to 8 ppm. And in ammonium salts, between 6 to 9 ppm. SH protons. Aliphatic SH resonates between 1 to 2 ppm. And aromatic SH resonates between 3.5 to 4.5 ppm. That's all in this lecture. Please subscribe my channel and press the bell icon if you like this video. Thank you.